So I will talk about self-explaining autonomous systems for better human-machine collaboration. And we will shortly see why we talk about human-machine collaboration and also why we need self-explaining systems. So that's my main motivation for this talk, is to show you why we need this and where the challenges lie, and where we can also benefit from insights from social sciences. So we have increasing automation and human-machine collaboration all over. We can see it in our working environments, in the production, where we have robots that help producing things. We have robots in warehouses where they go around and carry things and also manage all the logistics. We have robots in farming, so we can witness more and more autonomous farming vehicles that do many jobs there. We have computer or even robot-assisted surgery that is already used. We have already some autonomous driving vehicles, and we will have more in the future. And we also invite all these robots and autonomous systems into our homes when we use smart home devices, or if we, for example, have a robot vacuum cleaner or something like that. So the interesting question is, many of these applications are actually highly safety critical while we directly interact with robots. So if something goes wrong, they can actually injure us, and so we might get hurt or something. So we need to collaborate with them. We can't just avoid them, but they are quite opaque to us. So we don't know what they are doing and why they are doing it, unless we already have a lot of experience. So the interesting question is, do we trust those systems, and also can we trust them? And also, how can we actually achieve efficient collaboration with those systems? Because trust is necessary, but in the end we want to talk about efficiently collaborating with them and actually achieving our goals. So why do we need self-explaining systems? If humans interact with systems, no matter what kind of systems, they have mental models of the system, so they have some internal representation how they think the system works. And if the behavior of the system deviates from this mental model, so the actually observed behavior is not what we expected, then humans are confused. So one solution to that is to adjust the mental model of the human through explanations. So if the mental model and the actual system don't match, then we can try to change the mental model by providing explanations. So if we provide explanations, do we actually increase trust? This is an important question that is always asked in explainability research. And actually, there's a lot of empirical studies that investigate all this. Some find out that it actually is helpful to have explanations to increase trust, but not always. So there are actually situations where we can provide an explanation and it either has no effect on the trust, or maybe it can even decrease the trust. And why is that? Well, we have some kind of trust that we give to a system without already knowing the system. So we also heard about this in the keynote. So this is also called the dispositional trust. So that's the trust that we have from our experiences and so on. And with that, we go into the situation. And depending on what kind of person we are, we might have a lot of trust in autonomous systems because maybe we grew up with a lot of computer systems already, and we know, for example, that if we have any question, we can just ask Google and we will always get a good answer. So then we already have a lot of dispositional trust. And so if we then interact with the system, we apply this trust and just trust that the system will actually help us to achieve our goals. However, if we now provide an explanation that shows that the system is not totally sure in what it's doing, then we actually decrease this high dispositional trust that we had in the humans. So we have to be really careful in providing explanations. There's some research on trust, and I'm not a social scientist, so I actually don't know all of this, but there are three sources of variability in trust that we can have a look at. So this dispositional trust is how many trust do we bring in. Then there's also situational trust. So the trust may be different in different kinds of situations. So while we trust a robot in one situation, we might not trust it in another situation because the situation might be more dangerous for us, or we feel more uncertain in this situation, for example. And then there's this learned trust, which is basically what we can change by providing explanations, because this is trust that is achieved by interacting with the system, by seeing what the system is doing, and by also getting explanations on what it is doing and why it is doing. However, when we work on explanations, we want to go a bit away from this trust and say, okay, if explanations not always increase trust, then of course we should be careful when to give explanations and also what kind of explanations. And what we as computer scientists want to do is that the agent can actually help to achieve the individual goals. So what we do is we measure efficiency and performance and see if explanations can increase this. So it's just like another measure that we can take. But we have to be careful, and that's why we have to see when do we actually need an explanation. We know that humans explain events mostly then when they are surprising and negative. So if we feel that someone might not see this as a positive thing, what we did, for example, then we try to justify our behavior so that others see us more positive. And we can apply similar things also in machines. So we only explain behavior that is unexpected, because everything else seems to be matching between the mental model and the system behavior, and we don't need to explain this. But what kind of situations are actually unexpected? Well, we analyzed some interactions between humans and smart homes, and we saw that there are three categories of situations that need an explanation. So one thing is, of course, failures. So if the system fails, or also if the user fails. So for example, the user might use the system wrongly, and then the user perceives that the system actually fails, but the system works correctly. The user just don't know how to start the correct functionality. Then there is disobedience, which seems to be similar to system failures because the system is not doing what it should do from the perspective of the user, but it's actually correct behavior, and it might be because there are some system conditions that the user does not know. So for example, the coffee machine cannot produce coffee if there's no coffee in the coffee machine. Or it might be some contextual conditions. So if we, for example, ask the robot to put our laundry outside so that it can dry, but the robot knows that it will start raining in a few minutes, then the robot might actually not go outside. Or there might also be conflicts. So for example, if we have a goal where we say we want to save energy, and then we order the system to do something that consumes energy, then we have a goal conflict, and the system might, that's why not actually do what we wanted. Or we might also have conflicts with other users in a smart home. And the last class is context-aware behavior. So any behavior of the system that we not started, but that was started by some context conditions, some events that happened that trigger the system to do something. So any kind of autonomous action that the system performs, or also suggestions from the system that depend on context values. So in these cases, we need explanations, And there are also some factors that influence how much explanation we need. So this is complexity. If we have a more complex system behavior, then we also need more explanations. It's also cost. So if the robot is doing something that is costly, or if it's something where if it goes wrong, we might have high costs, then we also ask for more explanations. And also if it's something that occurs really rarely. So if it's something that occurs in a regular kind of basis, then we don't need so many explanations anymore because we're already kind of used to the behavior. So we might only need a short reminder. But if it's something that happens really rarely, like once a year or once every 10 years or something, then we actually might need the same explanation every time. One way to find out if the current system behavior is actually unexpected is anomaly classification. I did some work on this as well. The idea was that we have a look at the systems as a black box. So we actually don't know what the system is doing, but from observing the behavior of the system and some context data, we can then identify behavior that is not normal. And if we then also classify this behavior into different classes, like for example, behavior that depends on sensor failures or behavior that an autonomous car, for example, is doing always when there's an obstacle, then we already get some hint into the direction of why the system is doing this strange behavior now. So this is just one way how computer scientists could go to find out if the current behavior is actually unexpected. Another way is actually to have a white box system so that we know the system, we can look inside the system and analyze the system behavior to find situations where we need explanations because they might be unexpected to the user. However, we also need to consider context and recipients if we provide explanations. So the type of system interaction might be relevant to decide what kind of explanations we want to give. So for example, if a user is driving in a car, he needs to have a look at the street and he can't just provide some textual explanation, but then we would need to provide explanations, for example, via voice. Also time criticality, if the user has to do a decision, then he needs a short explanation. If it's not time critical, we can also provide longer explanations. Things like prior occurrence, I already mentioned that. And we also have to look at the recipient because we won't give the same explanation, for example, to a young child, to an elderly person, to the designer of similar systems, or a user that had no prior experience with similar systems at all. So we actually need to have a look at the recipient of the explanation and consider all these things. We might also need to consider certain preference, so what kind of explanation does this kind of user prefers, the abilities of the user, and also maybe some fears. So if we already know what this user has for fears with certain system types, so maybe it fears that it will lose this job due to this robot, then we might need to give a different kind of explanation. The idea here is first that we can adapt the human mental model with all these explanations, but actually we also need to consider if we might not even adapt the machine, because of course the human can adapt more easily, but we don't want to give all this burden to the human. We should actually also adapt the machine so that it is more transparent and works more according to the mental model that the humans have of the system. So what kind of explanation do we want to give? Well, let's consider an example. Here we have a robot driving in a corridor, and there is a door that might go open, but currently it's closed. But the robot knows that it has to avoid these doors, and so it will go a bit into the direction of the human and then go back again. So now the human might be confused because why is the robot going into his direction? There's no visible obstacle. And then we could provide a more technical explanation, which is quite easy to get because we can just extracted from system information that we already have. So it's a kind of heat map that shows the areas that the robot is not allowed to enter, and then it becomes clear why the robot chooses the way it does. However, this is not an explanation that we can give to any end user, so we might actually decide to not explain this by some heat map or technical details, but just give a natural language explanation saying, okay, sorry, I will not bump into you, I'm just avoiding the door because it may suddenly open. To build all this, we need to develop a framework that allows us as computer scientists to make systems really self-explainable. So we have already a lot of experience with self-adaptive systems, so systems that can adapt themselves to various context conditions. And we now want to move on to self-explainable systems, so systems that can monitor the system behavior, the recipient, the context, and so on, and then analyze whether an explanation is needed and what kind of explanation. Then first build the abstract explanation, which is basically the picture that we just had, and then build an explanation that is suitable for the recipient. And all this is based on some models that we need to use to construct those explanations. And we always like to construct those models out of something that already exists. And we did some work on that as well. So extracting explanation models from system models that are already there. So I already mentioned that. So coming to the end of my talk, we actually need to collaborate with social scientists because we have a lot of questions that we need some answers for, so that we are able to design good explanations and provide them at the right time and in the right way. So yeah, I already talked a lot about the questions for explainability. I also want to mention that explanations may also affect safety, hopefully in a positive way, but maybe also in a negative way. So we should actually also talk about this with people who know how humans will react to certain things. So if you have questions, I'm happy to answer them. Thank you.
Thank you so much, Verena. And I really appreciate your final slide, initiating conversations across disciplines. So I think a big thank you to you, not only for sticking to time, sticking to the topic, but also highlighting how relevant your work is to other fields, and for initiating a dialogue. Obviously, you and I are already in that dialogue. So Verena and I are working on a project on explainability in AI. And I thought it might be useful to just flesh that concept of the recipient's level of expertise a little bit more, because I really think, first of all, I like the idea that you're saying that it's not a one size fits all. And I think that probably explains why there is debate in the field as to whether explainability, more information is always more. And so I sort of wanted to capture that with my question, which is, on the one hand, with regards to expertise, if it's expertise as judged subjectively, I am an expert, I know how technology should work, I need a high level explanation. But actually, in fact, their capabilities are lower than they expect. This is coming from a psychologist, where we know there's this bias, right? An egotistical bias that we know more than we think we know. Will you tailor solutions as a function of what people think they know or what they actually know? And I don't know if that's too hard a question to give you on the spot, but when you mentioned expertise, and obviously because of what we've been working on in the background, I think it's an interesting one.
It definitely is. So I think there are many ways to approach this. So my first way would to just try to put users or recipients into some kind of categories. So we could say we have a designer of similar systems that we should know, for example. But if we actually are able to build systems that can observe the people, then maybe the system can actually infer or learn the expertise of the user. So then we could actually use the real expertise that is observable. But I think in the beginning we have to use the expertise that people think they have, because that's what they can tell us.
And I then had another quick question. Well, maybe it's not so quick. You've obviously tried to draw a clear link between explainability and what I would say is an acceptance of technology, which probably depends on trust. But I'm curious, because the example you showed and talked about is primarily about the capability, explaining the capabilities of the autonomous agents. Do you think that there needs to be some explicit explaining of the intention of the agents, like that they're definitely not going to do you harm, the more the benevolence side of the trust equation? So do you think explainability should be limited to capabilities, or do you think that it should include intention in some way?
I think it should also include intention. It's a bit harder from a computer scientist view, of course, to
well, I was thinking about your robot example, right, with the door. Is that they're, on top of the heat map of where they're allowed to go, implicit in that is that they don't want to hurt the human, right? So that's where the benevolence aspect. And I'm just wondering whether you would make that point explicit when explaining it, or do you think it's sufficient that you just sort of give them this overall map or set of rules, and it's up to the user to realize, to extract out that not only is the robot capable of navigating the hallway, but they also will avoid, they don't want to cause harm. I ask this because, we just want, one of the key questions of our session today and tomorrow is to determine whether we use the same contract, the same criteria for the contract of trust for humans and autonomous agents. And the assumption, at least between humans and human interactions, is that we also want to know that they are trustworthy at the level of benevolence, how they are at the subjective level. So I'm just curious whether you think this is necessary in these cases.
I think in cases where we really talk about humans and robots, it is necessary. I actually consider it avoiding to hurt humans should be a goal that is always present in robots. It's also part of the famous robot laws. So that's why maybe I didn't mention it before, but of course this is something that is very important and should always be mentioned. And I think if we have a heat map like this, then we could also have semantic rules that actually were used to create this heat map for the robot. So if we know that, for example, one semantic rule in this case would be to always keep a certain safety distance from the human. Another rule would be to always stay on the right in a corridor, and a third rule would be to avoid doors because they could suddenly open. And if we give this set of rules and then also the heat map, and then maybe also highlight the rule that is currently active, this would actually really help the humans to understand the robot and to anticipate what the robot will do in other situations.
Thank you. Thanks very much. That was a more comprehensive answer than I expected, because I think it's such a, you just don't know, right? It's a very, very tricky one to know if it's going to help or not. If you open up that Pandora's box and start talking about the benevolence of robots, are you tapping into people's fears? So I really appreciate the answer. Thank you so much. And I'll just take that moment again to thank you for your wonderful talk and for joining us today on this Social Bridges event on trust.